Hello guys, welcome to another video, and today we will try to solve the following integral. The integral of the square root of x multiplied by the square root of x multiplied by the square root of x multiplied by the square root of x, and so on and so forth up to infinity with respect to x. Now, as you can see, we have here an infinite nested radical in which we take the square root of x, then multiply it by the square root of x, and then we keep doing this all the way up to infinity. Now, it might not be obvious at first, but there's a trick that we can use here in order for us to simplify this integral tremendously. And so with that, let us now start our solution. Now notice that each and every radicals, or to be more specific, each and every square roots that we have in our integrand can be rewritten as a fractional power, which is 1/2 in this case. So we can rewrite our integral as the integral of parentheses x, right, multiplied by x, multiplied by x, multiplied by x all the way up to infinity, raised to 1/2, and then raised to 1/2, raised to 1/2, and raised to 1/2, right, with respect to x. Now, by the rules of exponent, if we have any number or any term, let's say ab, that is raised to some power, which is m, let's say, this can be rewritten as a raised to m multiplied by b raised to m, right? Now, if we would take a look into our integrand, we have here two variables that is being multiplied within this first square root, okay? Within this first square root, right? In which our first term is x, right? As you can see. And then our second term is this infinite product, right? Or infinite nested radical, right? So we can apply this rule into our integrand here, and then we would get that the integral of this will become x raised to 1/2, then multiplied by x, multiplied by x, multiplied by x all the way up to infinity, raised to 1/2, raised to 1/2, and then raised to 1/4, right? Since what we did is we multiply this power into the exponent of x, which is 1, which will become 1/2, since 1/2 times 1 is just 1/2, and then multiply 1/2 to the exponent or the power of this term, which is 1/2, which is 1/2 times 1/2, it would become 1/4, okay? And this is with respect to x. And then, as you can see, we can also apply the same rule in this case, right? In which within this fourth root, we have two terms being multiplied. The first term being x, and the second term being this infinitely many products, right? So applying it again, this will become the integral of x raised to 1/2 multiplied by x raised to 1/4 multiplied by x all the way up to infinity, raised to 1/2, raised to 1/4 times 1/2 is 1/8 with respect to x. Now then again, same thing, right? First term being x and the second term being this infinitely many products. So let's apply this rule again. This would give us the integral of x raised to 1/2 multiplied by x raised to 1/4 multiplied by x raised to 1/8, right? Multiplied by, so 1/8 times 1/2 is 1/16, right? So x raised to 1/16, okay? And we will keep doing this pattern or this rule all the way up to infinity. So this goes on to infinity with respect to x. Okay, so we just keep multiplying infinitely many 1/2 into our main exponent here, right? So okay. Now, as you can see, all of these terms that are being multiplied to each other has a same base, right? Which is x. So by the rules of exponent, if we have, say, any number, a raised to m, multiplied to a raised to n, this will be the same thing as a raised to m plus n, right? So we can use this rule in our integrand, and this will become, okay, this will become the integral of x raised to 1/2 plus, next is 1/4, plus 1/8, plus, of course, 1/16, and so on and so forth up to infinity with respect to x. Okay, now all we have to do now is evaluate this infinite series. But what is it? Well, if you would notice that each and every term within the series has a common ratio, right, of 1/2, each and every consecutive, okay, terms within the series. In which you would notice that if we would look at the first term, which is 1/2, and then you multiply it by itself, which is 1/2, it will be 1/4, leading us to our next term. Then multiplied by 1/2, it will give us the third term, which is 1/8. Then 1/2 will be 1/16. And of course, if you might guess, the next term will be 1/32 by multiplying this by 1/2, and so on and so forth up to infinity. So what we have here is an infinite geometric series with a common ratio of 1/2. So what is the formula for the infinite geometric series? Well, our formula is S, right? S sub infinity is equal to a sub 1 over 1 minus r whenever the absolute value of r is less than 1, right? Now, our first term here, which is a sub 1, right, is equal to 1/2, right? That's our first term in our infinite geometric series, right? This. And then our common ratio here, which is r, is also 1/2, right? And since our absolute value of r, which is just 1/2, is less than 1, right? If we take the absolute value of 1/2, it will just be less than 1, right? Then this means we can use this formula, okay? So, plugging this in, this would give us that the infinite series, okay, or S sub infinity, is equal to 1/2 all over 1 minus 1/2. Now, 1 minus 1/2 is just 1/2. So this will become S sub infinity is equals to 1/2 all over 1/2. Okay. Now 1/2 divided by 1/2 is just 1. So we would get that the infinite series is just 1. Okay. Now, this means that the infinite series that we have here is just equal to 1 as we've calculated. So we can rewrite this integral as the integral of x raised to 1 dx. Right? Did you get that? Since we've calculated that this infinite series is equal to 1. So this will become the integral of x raised to 1 with respect to x. Right? So and this is good. So this would just basically become the integral of x dx. Then we can apply a simple power rule of integration, giving us the integral is x squared over 2 plus c. And there you have it. This is the answer of this integral, and we are now done.